Happy New Year and welcome back to campus. Uh, Today we will go over introductory material, mostly class mechanics, and then jump right into introduction. So this is Computer Networking, CSCI 331. I'm Dr. Holness. So we will be using the book, Computer Networking, A Top-Down Approach, the 7th edition by Carosa and Ross. It's fairly comprehensive, uses Python for examples for the application layer, and it's the most widely used computer networking text in the world at the moment. There's also a great companion website, and this text also gives good coverage to current developments, specifically software-defined networking. And so because you're here, certainly you know when the class meets, Tuesday, Thursday, from 12 noon to 1:15 p.m. using my WebEx meeting room. There's the URL. Office hours, tentatively, and this might change depending on how the semester plays out. Office hours will be Wednesday from 10 a.m. to 11 a.m., and then also Wednesday from 11 a.m. to 12 noon. Now, again, this is subject to change depending on how the semester plays out. And so, email, there's my email address, jholness@desu.edu. I would prefer you use the Slack channel. The Slack channel created for the course is CSCI 330, and it is linked through the course Blackboard site. My number, 302-857-7932. I can certainly retrieve that. I also purchased a Google Voice account and got a pretty nice number, which looks like it's an on-campus number, but it's not, 302-857-0012. So that Google Voice is different or new for this semester. The assessments, we will have 4 homework assignments. They could be written, they could include programming, will be a total of 5% each for a total of 20%, 5 project assignments, 5% each for a total of 25%, 2 written exams, 12.5% each for a total of 25%, a research project, which will be the final exam. The report, experiments, and code will be 20%, and the presentation 5%. Class participation will be 5%, and extra credit if you participate in a cyber competition, you will get an extra credit of 5%, but you must furnish proof of your participation. The grading scale is absolute. My late policy, I do not accept late work. Those of you who've had me for class before are familiar with this. Those of you for operating systems, those of you who have not had me for class, no late assignments. Once the assignment comes due, the submission link will go away, and I do not accept late work, so manage your time appropriately. All programs that you write must compile, link, and run in order to receive credit. I'm not product support. It will be 0, and I'll just move on. Please make sure you read the syllabus, the schedule. I spent time painstakingly to lay out the schedule for this course for the entire semester because it has so many moving parts, and make sure you check the Slack channel frequently and the Blackboard site for the course frequently. Office hours. Now, to make good use of office hours, help me to help you in the best way possible. Please make use of the scheduled times. The office hours that are posted do not require you to make an appointment. You just say, hey, I have a question. I'd like you to use Slack first so I can initiate a WebEx session with you if needed. I can do that from within Slack. We have WebEx installed within Slack. But if you cannot make the posted office hours, or for whatever reason, be that a class, scheduling conflicts, what have you, arrange an appointment ahead of time, either by email, preferred, or by Slack as well. And that allows me to pull up my calendar so I can choose a time that's mutually agreeable. I can help you the best that I can. I frequently lurk on the Slack channel several nights a week and often interact with students. Have in the past, I plan to do so this semester as well. Interact with students in the evenings on Slack quite often on various topics concerning homework, projects, etc. I'm more than happy to help you be successful, but please help me to help you. Now, I'm regularly working a lot of time during the week on something else, and it's hard to help you if I'm in the middle of something else. What is helpful to me is for you to provide context about what the issue is. If you say it doesn't work, well, I'll ask you, well, what is the it you're working on? If you are having difficulty understanding a concept, please tell me what the concept is, provide some context. I have a lot of other classes I'm teaching and a lot of other activities, and it allows me to put my mind in the right context to help you the best way that I can. What does it take to be successful in this class? Because, no faculty member enjoys when a student does not do well. Well, here are some best practices. Start your assignment right away. As soon as it's assigned, look at it, think about it. Do some of the reading every single day. It doesn't require a lot, 8 to 10 pages a day. It's not a lot. Will take you half an hour to 40 minutes. Write things down. That kinesthetic learning, you want to make sure that you're not just viewing it, you're writing it. So whether it's electronically, you're taking notes, whether you're doing it on a pen, with a pen and paper, I prefer pen and paper, write things down. Explain it to someone else. Form study groups with a group of people in the class and take turns explaining it to one another, holding each other accountable. And the best way to understand the material or to test your understanding is to explain it to someone else. Start thinking about the material in chunks every single day. Now, this course, my expectation is that you'll invest at least 1 hour a day in the material, regardless of if there's work that day or not. Just because you don't have an assignment doesn't mean that you shouldn't be doing work in the class every single day, at least an hour a day. There are ample reference materials out there if you need refreshers on various things. Discuss the concepts with your classmate and really think about what you're being asked to do before you act. Understand the question before you answer it, abstract the problems, and design your experiments that we'll have or programs before you code it. Don't just jump right in without thinking about what you're doing. So basically work hard every single day. And so this one, for any faculty member, it's not fun, and I do not take pleasure when a student fails the course if a student does fail my course. Now, the biggest reasons that people are not successful in this course, I'll just outline them. Not handing in work is the biggest reason, or one of them. And a 0, which you receive if you don't hand something in, on any component is very devastating to your grade. So for this class, each homework is worth 5% and each project is worth 5%. So let's say you miss 2 homeworks and 1 project. So that homework is 5%, project is 5%. So this missing the 2 homeworks and 1 project means that you get a 0 for 15% of your grade. So after this happens, if this happens, this means that the best you can do is an 85% in the course, which is a B. Now, there's a caveat for that B. That B is the best you can do provided you get 100 perfect score on everything else. So if you make any other mistakes beyond just not handing in 2 homeworks and a project, it's very likely you're going to score far below a B. It's really hard to get 100% on everything. So that being said, make sure you manage your deadlines. I will always make you aware every single class what is due, as well as make your deadlines and do your work every single day. It is not a recipe for success if you wait until something is due, wait a day or 2 before something is due to start trying to do the reading and do the homework. You will not be successful. This will require you to pace yourself and plan your time, manage your schedule appropriately. The other reason is not following instructions. So there are quite a few of you in the class. Last time I checked the roster, it was 23 of you. And I have very specific instructions associated with the assignments. Some of these I'll outline here. Other of them I state specifically on the homework. Now, not following instructions is another reason, and I'm going to have to be very strict this time. Sometimes I gave people leeway last semester, but I'm going to be very strict because there are so many of you. When you do not follow instructions, it slows down the grading tremendously. So when I say a single document file, MS Word or PDF only, I mean a single document. Don't hand in 5 or 6 images, JPEGs, and expect me to assemble it into a document so that I can read your submission. I'm not going to do that. I'm just going to give you a 0 and move on. So make sure you take the time to hand in a single MS Word or PDF document only. If you're using Star Office or you're using Apple's Pages, do a save as and save as a PDF or save as an MS Word file. Okay. Also, make sure that what you're saving actually contains information. Read the document that you saved before you hand it in, because I only see what is downloaded from Blackboard after you've handed it in. When I say to produce an archive, I'll say archive using zip only. Don't use RAR, don't use TAR, don't use 7-zip, none of those formats. If you have a zip archive for a submission that's not in zip, I'm not going to bother. I'm just going to say 0 and move on. All your programs must compile and run. I'm not going to sit and debug your programs. So it's really important that you include in your submission every single piece of code or data file that is needed to run your program. Do not have your program prompt for input. It must run completely from start to beginning without requiring user input, and don't assume that you have a certain path set up on your machine, because what I get is exactly the archive that you hand in. So make sure that your program compiles and runs. And one way to test that is before submitting your program to actually take the archive or zip file that contains your code and data and unzip it to a new location and test if that thing you intend to hand in actually runs. Now, managing all of the files, and there are 23, probably 24 of you, 23 last time I checked, that's a lot of different files to manage. So I will be asking you to put all of your work in a folder with your first name and last name as the name of the folder. So if your name is John Smith, it will be John Smith as a folder name. So that way, when you archive it, I will unzip it when I download it, and there will be a folder with your name. Don't just put files in an archive. Put everything in a folder or directory first and zip everything in that directory. So when you zip it, and I say put your work in a folder and zip it, I mean put your work in the folder and zip it. I'm not going to sit there and chase after your files in order to assemble your assignment. Non-standardization slows the grading immensely, and I will deduct significant points for not following instructions. I did that to some degree last semester, but I have too many students in my class to do that this semester. So please make sure you're giving yourself the time and follow the instructions. Have pride in what you're doing and don't do sloppy work. Now, it doesn't bother me. You can hate me now, but you're going to thank me later that I hold you to these standards. And I have several letters that students have sent me over the years and several emails to prove it. Gosh, Dr. Holness, thank you for being so hard on us because it helped me immensely when I hit the ground running in my career. Another reason why people fail this course is poor time management. You might think, gosh, well, okay, it's only 8 pages a day. It's not that bad. It's a little bit. Let me wait a week until we have something due. That's going to be a recipe for disaster. It builds up very quickly if you're not doing something every day. So when you get an assignment, everything needed to do the assignment is given to you in bits over time. So look at the assignment as soon as it's released. If I give you a week to work on it, it means it's going to take you a week to do it. That doesn't mean you wait 2 days before it's due to start it. You're going to need that week to really think about things. Do not cut corners as well. I'm not stupid. I know that there are answers floating around on the internet, and yes, I do check. I check it every single assignment. And every single year, I catch and penalize people for cheating. Don't be one of those people. Just do your work. The homework and projects are there for you to learn. It's a useless exercise to think that you're going to copy things off the internet. I know all the sites, and I check them, and think that I'm not going to catch that. Also, make sure that you are answering incomplete answers. Don't just put the answer. I need to see the development of your answer and how you arrived upon an answer, because I'm well aware of all the things people are copying and pasting from off the internet. I take honesty very seriously. So please do not put me in the uncomfortable position of failing you. I have no qualms about it, nothing personal. Make sure you do your own work, and the work that you submit reflects your own work, not the work of your peers and not the work that you've copied off of the dozen or 24 different homework banks that are floating around on the internet. Cheating. And I'll stress this again, do your own work. Don't make my job harder. Do not copy solutions from the internet, solution guides, friends here or other universities, or off classmates. If you copy off a classmate, both people will get the failure, both you and the person that made the information available to you. Do not share your programming code with others, and I reserve the right to question suspicious work and ask you to demonstrate that mastery. Nothing personal, but do your own work. You can collaborate. Feel free to discuss algorithms that you see in the textbook. Discuss with your peers, your colleagues, what you've read in the textbook. You can help a classmate to understand what a problem statement means, but you do not give him or her the answer. You can show your classmate how to run, for example, a Python editor, but you don't give him or her your Python code. So make sure that you do your own work, and if you have any question about whether a collaboration encroaches on cheating, please feel free to reach out to me to clarify that. So what this course concerns is educating you for a career and not a vocation. And what do I mean by that? We will go over a complete, rigorous coverage of the major topics in computer networking. You will develop mastery of scientific, engineering, and design issues concerning computer networking. You'll gain experience in several concepts employed by applications that use networks, so-called distributed applications. You'll also gain experience in the assessment, experimental design, triage, diagnosis, and understanding of trade-offs for repair of networking infrastructure. And you'll effectively understand the physics of computer networks. So what do I mean by the physics? I mean you have a number of components, understand how they operate, how they interact, and those forces between them that give rise to some global behavior of the collection of parts that you choose. So this is what this course is not. In this course, you will not learn how to configure a Cisco network. You will not learn how to assemble computer networks. You will not learn the defunct 7-layer ISO model. You will not learn application frameworks. There are many course alumni. This is just a very small sample of all of the things course alumni for this course are doing who directly use what you will be learning this semester. Now, I hope to be able to add your experience or your landing place post-DSU to this page. So the first thing we're going to talk about and we'll make use of throughout the course of the semester is a packet analyzer, or a so-called packet sniffer as it's called. And we'll be using a very widely used tool called Wireshark. So let's talk a little bit about what this packet sniffer does. So we have a typical network, and we have some machine connected to what you probably call a router. And after this course is done, you will no longer call this a router. But nonetheless, at this juncture, you have this box router, and you plug in your computer using an Ethernet cable, category 5 cable, to connect your machine, your box, or device to the network. Now, on your machine is running Wireshark, and inside the OS, we have a number of layers of functionality that are running to give you or implement your access or exchange of data across the network. Now, of course, you have in these components managed by the operating system, you have what's called the physical layer, link layer, network layer, transport layer, and these will be covered extensively throughout the course of the semester. But these are all aspects of the network that are managed by the operating system. They live in the operating system. And on top of that, we have the application layer, and these are things like your web browser and your email client, or webmail if you're using webmail. Now, running on your system is Wireshark, and it consists of two components. One component is called the packet capture driver, and that runs in the operating system. And The other is called the packet analyzer, and it runs in the application layer as an application. Now, packet capture, as its name implies, or from the name, you might surmise that it obtains or captures a copy of all of the chunks of data, Ethernet frames, that are sent to your machine inbound or sourced by your machine outbound. And so all of those chunks or units of data on and off your machine are obtained by this packet capture driver called PCAP. Now, of course, if you're using Microsoft Windows, it's WinPCAP. Linux has a packet capture. It's using the device file. Mac OS is using the device file. Now, all of these chunks of data, as they're called, packets, are then sent to the packet analyzer, and the packet analyzer has been programmed to interpret what these packets mean and how they look, and it displays to you in the correct formatting all the information for the packets. Now, what this Wireshark packet sniffer will do for us, it'll allow us to instrument actual computer networks. Now, certainly if we're on campus, primarily, we do a lot more experiments pertaining to campus, but because we are virtual this semester, the experiments will be tuned, the extra stuff, for a home network type of environment or a coffee shop or something like that, if you choose to. So what this packet analyzer does, it allows you to literally visualize and sample all of the packet or data that's trafficking on a network. Now, in doing so, it gives you a first-hand experience in the instrumentation of a network. And the approach taken by the textbook, Computer Networking, a top-down approach, is to allow you to understand computer networks by instrumenting them and diagnosing them. And so we'll have a bunch of assignments, projects, where you'll be using Wireshark to examine the result of all sorts of experimental tasks for each one, or exercising each one of these layers: application layer, transport network, link, or physical layer. So this is Wireshark, and the first assignment is to get you bootstrapped in installing and using Wireshark, and to figure out how to install it. You're all adults now, you're juniors and seniors. Go to wireshark.org and follow the instructions. Okay, so let's jump right in. Let's get started. Chapter 1 in the text, Computer Networking, a top-down approach, is purposed with giving you a high-level overview of what a computer network is. Now, this has a number of purposes, such as introducing you to the terminology. Every discipline in every aspect or subfield within computer science and IT has professionally accepted terms. And so one of the goals is then to teach you what this vocabulary is. And the reason why that's important is so that you can have appropriate conversations about the particular aspects of the computer network with the professional and engineering and scientific community. The other goal is to give you sufficient amount of depth so that you understand at a high level what the pieces are, at a high level how they interact, so that when you go into greater detail in subsequent chapters, you understand where things fit in. And so the approach that the text takes, and we will adopt that approach using Wireshark as well as the text itself, is to use the internet as an example. Why the internet? Because it's already around you, so it grounds it out into things with which you already have experience. And so we'll talk about what the internet is, what a protocol is, look at the various components, the network edge, the network core, and we'll look at performance characteristics, things like loss, delay, and throughput. We will look a little bit at high level into security. Now, certainly you could have 1 or 2 semesters just on network security. We only will barely scratch the surface in this class with network security. We're not going to go into great detail because you could spend an entire semester on network security alone, and we certainly have courses in the division that cover that. We'll look at the layer and service model, but we will not, depending on time, probably won't look at history. It's very interesting to read about internet history. I encourage you to do that on your own time, but I won't hold you responsible for it in this class. So let's take a look at what the network is. So this diagram you'll see quite often throughout the book, and we'll talk about the nuts and bolts view about what they do. So we have these clouds, and these clouds, we have one entitled mobile network, we have a home network, we have an institutional network. Now, these are different types of networks. Mobile network you're familiar with. Maybe it's Wi-Fi, or maybe it's the cell phone network. Home network, that's your typical setup with a service provider like Verizon Fios or Comcast Infinity. Many of you are probably using those. Then the institutional network is more like what you'd see on campus at DSU. You have a large number of devices attached to the network, and you have a whole complicated array of devices whose responsibility is to forward chunks of data between machines that are trying to communicate both across the network as well as off the network. Okay. And we also have your ISPs, Internet Service Providers. We have our regional ISP, and we have our global ISP. The regional ISP serves in a location like, say, in Delaware or in parts of Delaware. Global would be connecting the East Coast to the West Coast, or the East Coast of the United States to the African continent, the West Coast of the African continent, for example. So we have lots and lots of devices, billions of connected devices. We have computing devices. We have other devices like washing machines and refrigerators. And each one of these devices is called a host or an end system. It's called an end system because if you look at this diagram of the internet, on one end of the network, if you were to kind of draw a big blob or cloud surrounding all of the parts of the internet, at one end you have a mobile device, for example, like a laptop. At the other end, you might have, for example, a server. And so in the text, we use as synonyms the word host. It's called a host because applications run on them or are hosted by these. And it's called an end system because it exists physically at the ends or the edges of the network. Now, oftentimes in the literature, you'll also see the term network edge. And edge means end system. It's at the extreme, at the border, if you will, of this internet. And so each one of these hosts or end systems is running an application. And these applications exchange information with one another across the network. And these pieces of the applications, one part might be running on your laptop, another part might be running on your server. Together, they interact with one another across the network to give you the illusion of a single application. And so you also have these links here, these lines, and these links represent communications. They're channels through which chunks or units of data can be passed, regardless of what that data is. It could be video data, it could be image data, it could be audio data, it could be voice data, what have you. And so these links can be implemented in a number of different ways. You can have fiber optic cables, so passing data encoded as frequencies of light. You can have radio signals, so that's electromagnetic information, electromagnetic radiation, if you will, or electromagnetic energy propagating through the airwaves. That's what wireless does, be that Wi-Fi or cell phone. You can also have copper, right? This is a network cable, is twisted pair of copper wire. Now, of course, you can also have satellite, right? So with satellite, you're taking your data, you're transmitting it wirelessly to a satellite orbiting above the Earth, and then it takes that signal and then it bounces it down to another location on the Earth. And so one of the things that you're concerned with these links is something called the transmission rate. And the term used for that is bandwidth. Because of the physical characteristics of the link, and it could be the material characteristics, could be the noise, what have you, the interference associated with it, you're going to have different rates of transmission. Now, of course, the higher the transmission rate or the bandwidth, the more data you can send. And when you purchase, for example, a subscription from, say, Verizon Fios, what you're paying for is you're paying for bandwidth, the increased transmission rate. All right. So the other type of device that's not an end system or host is a so-called packet switch. And these packet switches are depicted as these circular disks with the X through them. And these specifically are routers, but more generally, we'll give it the term packet switch because we can have a router and something called a switch, which we'll talk about, a layer 2 device. And the whole purpose of these packet switches is to take one of these units of data, to store them, to evaluate them based on certain pieces of data, which we'll talk about, and then based on that evaluation to forward them out some other link. And so it's these packet switches that are connected together, both to the end systems as well as to one another, that implement the ability to send data across the network. And so let's say you sourced a message at this host. You would store it in this packet switch. It would evaluate it, forward it. It would be stored by this one, evaluate, forward it, store it, 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 and forward it, and send it out. And next thing you know, your laptop wirelessly over the cell phone network gets that data. And so the packet switch's responsibility is the storing and forwarding of these units or chunks of data that we're calling packets. And in aggregate, the storing and forwarding across all of these routers in our so-called switching fabric implements our ability to exchange data between end systems regardless of which ones they are. It's quite amazing that this happens. So it's not amazing, it's system engineering involved. So there are several internet-connected devices, things that might measure your power usage, things that might measure whether or not you're lying down in bed or moving. That could be, for example, very useful for infants as well as for hospitalized patients. Internet phones is something that's very useful. You can have the same phone number, like Magic Jack, and use it anywhere in the world. More recently, there are all sorts of other smart devices, internet-connected devices, Smart Lock by Amazon, and the idea there is that when the Amazon delivery driver comes to the house, and this is something that you can buy now, instead of leaving it on the front step, they can open up your door, put in your delivery inside your house, close the door, and then the door locks. So you can have, or grant temporary access to the delivery driver to put your package inside of the house. Now, certainly, I don't feel comfortable doing that, but there are many people who do that. You have Wi-Fi light bulbs, internet-connected light bulbs. The interesting part about these things is not only can you control the type of light, if it's bright light, dim light, colored light, and so forth, but you can also set schedules for when your lights turn on and off. So let's say you're working or you're at school and you're going to be at school later than you imagined. You can turn on the lights inside the house or on the front step or porch or what have you before you return home from the comforts of the dorm room or comforts of the library, for example. You also have internet-connected appliances like washing machines. You can monitor the progress. Maybe you put in a load of clothes before you leave to school in the morning, say you're commuting, and then you might set the washer going so that your clothes are washed and cleaned by the time you get home. And you can actually look at the progress of that wash cycle. So in the nuts and bolts view, when we look at what the internet is, it's a network of networks, a set of interconnected networks. And this is done through a set of interconnected ISPs. And so in this diagram, going back to it, we have our institutional network. That's something like DSU's network. We have your home network, and that's typical setup like through Verizon Fios or Comcast and Xfinity. And then you have a mobile network, something that might be using the cell phone's 4G, 5G standard. And so each one of these networks is connected to one another through these ISPs. You might have your mobile network connected in through a global ISP, home network through a regional, and maybe DSU's institutional network through regional. And that regional ISP is interconnected to other regional ISPs through the global ISP. So this internet is the connection of networks. It's a network networking together of different networks. And we need to have these things work, these applications work with one another. You need a set of standards or a scheme, if you will, of how they interact with one another. And these are your protocols. So you have the network of networks and you have your protocols, and these protocols control both the message format as well as the action taken in response to having certain messages occur. And so these protocols control the sending, receiving of messages. And there's certain standard protocols that are very popular: TCP, Transmission Control Protocol, IP, Internet Protocol, for routing, HTTP, Hypertext Transport Protocol. This is the foundation of the web. There are proprietary applications like Skype that have them. There are wireless access protocols, 802.11, which is the Wi-Fi standard. And there are other internet standards that are pre-agreed upon by certain organizations, methods for how you do certain things. Now, these internet standards are published through what are called RFCs, or requests for comments, and you can look them up. They're no secret. And they're managed by the IETF, the Internet Engineering Task Force. Now, I remember early in my career, I had opportunity to work with someone who was on the IETF for DHCP, the Dynamic Host Configuration Protocol. It was just absolutely amazing working with this person. But that being said, without these standards, these protocols would not work. To use a physical example, imagine if when you gas up your automobile, right, all of the gas tank entrances, all right, for gassing up your car, for filling your car with gas, they're standard, right? They're a certain diameter, and they have a certain angle of bend to them. Now, you could imagine, what if there was no standard for the nozzle to pump gas and for the gas tank access to accept the gas? So that would mean, if there was no standard, what if somebody had a square gas pump nozzle? What if someone had a triangular gas pump nozzle? What if somebody had a round gas pump nozzle? And what if they were bent in different angles? So that would mean that if you have certain cars, you could only go to certain gas stations. That would be an absolute mess. But because we've standardized on the gas nozzle and the gas tank access, it means that any car can go to any gas station. And that's the same thing that these internet standards do. If you are implementing a web browser, as long as your web browser adheres to the HTTP standard, your web browser can connect to any web server. And likewise, if you have a web server that adheres to the server responsibility of HTTP, your web server is guaranteed to work with any web browser. So these standards are really important in order to have applications that participate well in the internet. Okay. So the internet is also a type of services, right? There are components that provide some sort of capability to engage in certain types of behaviors to applications. And these are things like the web, voice over IP, email, games, e-commerce, etc. And it also provides a programmatic interface to applications that allow the applications to use the ability to send formatted pages or to send messages in the form of email. And so these programmatic interfaces, these APIs, application program interfaces, these provide the hooks that allow sending and receiving applications on these end systems to be able to connect to the internet and participate in this framework. It also provides service options. And so various services consist of certain guarantees, and you have different levels of service, and we'll see that quite a bit when we talk about the transport layer. So some in the transport layer some services are reliable, some are unreliable, and there are differences in terms of the speed as well as the guarantees, both in terms of unadulterated content, it doesn't get corrupted, and the management of the order of delivery of items, things like that. And so not only do we have the components, we also have the services that allow applications to participate in the sending and receiving of messages between end systems on different parts of the network. And so the next natural question is, what is a protocol? Now, of course, in human protocol, if I were to ask you, what's the time, um, you would answer me back. Or if I said, hey, I have a question, and then you say, yeah, what's your question? And then I go ahead and say the question, or you introduce yourself. Now, human protocols, we have specific messages that are sent, and based on these messages, the format of those messages and the content, we take certain actions in as a result. And so this set of messages, as well as their format and the actions that we take, that together is called a protocol. Now, for a computer network, you're dealing with machines rather than humans, and all communication activity in the internet is governed by protocols. Why? Because you need a scheme for how you specify the behaviors that the entities in the network engage in. So the protocols define the format, order of the messages sent and received among these components in the network, as well as the actions taken whenever you transmit a message or whenever you receive a message with a particular type of content and format. And so a human protocol and a computer network protocol are very similar. And so this screen depicts a standard protocol diagram. Now, in this protocol diagram, if you look at it, you'll have different columns, and one column will be each one of the entities in their interaction with one another. So let's call this person here Alice, and let's call this person here on the right Bob. Now, of course, this column Alice might be one machine and Bob might be another machine, but we're going to relate here the human protocol to the computer protocol. And so you'll notice here each column represents one of the hosts or entities on the network, not just hosts, could be a router, one of the entities or components on the network. Now we have a set of edges that traverse from one entity to the other. That's a message. And you'll notice here that message is slanted. It's not directly going horizontally left to right. Now, in this protocol diagram, we have, as I said before, the columns represent the two entities that are communicating. As you go down in that direction, that's time. So time increases in the downward direction. And so when we have an edge, like this first one from Alice to Bob, well, the content of the message says hi, so it's a greeting. And this message goes from Alice to Bob, but because you'll notice here that butt of the arrow, the tail of the arrow, starts at Alice, and as time increases, you'll see that it goes across to Bob. So that means the message starts with Alice and it ends at Bob. So we also make sure when we look at the protocol diagram, as we move from top to bottom going in the downward direction, that's time. Time increases going down. And so in this diagram, Alice initiates a hello message to Bob. Bob takes that message and then thinks about what that message means, and the action Bob takes is to send a hi message back. So once Alice gets the hello response back from Bob, Alice knows that Bob is ready to communicate. So then Alice initiates a new message, do you have the time? When Bob answered hi back to Alice, well, Bob said, okay, I'm awake, I can participate in whatever it is you're going to ask me to do. So Alice then says, do you have the time? Bob takes that message, understands what it means, and then in that period looks at his watch and then speaks back, it's 2 o'clock. Alice gets back that message and the interaction is done. And so one of the things that you'll see here, we have a message from Alice to Bob and a response back. That message that goes out and then a response back, that's called a round trip. And this first round trip is purpose with Alice establishing with Bob that Bob is ready to engage in some interaction. So then we have the actual message, which is the second round trip. Now, of course, Alice says, do you have the time? Bob looks at his watch, and then he returns back the time. Now, relating this to machines, well, we have that first round trip where we have host A and we have host B. This might be a client machine like a laptop, and this might be a server somewhere. So you initiate, for example, a connection request. Okay, hello, I'd like to make a connection. So then you have a connection response. Okay, well, I am ready to make that connection, so I'm going to respond back to you to say, okay, I'm ready. So at this juncture, host A knows that host B can engage in the interaction. So the second round trip, it says, okay, get the following web page, and the server takes that, does something, looking in its file system for the web page, and returns back the contents of the web page, and your web browser then draws that web page, and you have buttons and lists and pictures and so forth. So a network protocol is very much like a human protocol. You have round trips, you have establishment of communication, and then you have the communication itself. You get a message, you analyze it, and then you take some action, return back a response. Okay, so let's take a look at the network edge. Now, at the network edge, as we said, it's the extremes, the boundaries, if you will, of the network. It consists of clients and servers, hosts of different types, and we'll talk about what a client and a server means when we get to the application layer. And the servers often exist in data centers these days, but it doesn't have to, but many cases it does. You have so-called access networks and physical media. Now, of course, these access networks, they're called access networks because this is how your hosts gain entry or access to the network. Now, of course, on a mobile network, you're accessing the network based on wireless communication. With the home network, you're accessing the network. It could be wireless, it could be wired, but you're accessing it through that router that you establish through your service provider, through the regional ISP. Then you also have the network core. It's a bunch of interconnected packet switches or routers. And this is where the network of networks thing comes into play. So we have all of these components. And one of the things we want to know is how do you connect the end systems to the edge router? So here at the edge, you have an edge router connecting this mobile network. You have an edge router connecting the devices to access the network on the home network. And then you also have edge routers, these routers here on the enterprise network, connecting all of those end systems to the enterprise network. So you have different types of access networks, be that mobile, residential, or institutional, and you want to keep in mind about the bandwidth that you're going to need for these access networks, whether they're shared or they're dedicated. And so this is what an access network looked like at one point for home, a DSL or digital subscriber line. You can still get them, but it's dying out. And what DSL did is it took your telephone wire and it modulated or changed the frequency so that you could send data down this wire. And so here, your voice and data were transmitted at different frequencies over a dedicated line to something called the central office, which is a facility owned by the phone company. And so you had something called a DSLAM, a digital subscriber access multiplexer, and it was the job of this DSLAM to take the set of frequencies for voice and the set of frequencies for data from your computer, separate them out. Now, the data it would send through the internet, and the voice it would send through the telephone network. Now, of course, DSL is dying out, and coaxial or hybrid fiber coax is what really replaced it, or is more so replacing it, as well as satellite. And there's also something called fiber to the curb, which is what your Verizon Fios product is. And so the bandwidth for DSL lines was about 2.5 megabit per second. Typically, because of interference and bandwidth issues, you get about 1 megabit per second. Now, of course, because you're using copper wire, there's something called transmission loss with copper wire. And what this means is that the longer this length was between your home and the central office, well, copper wire is a conductor, but it also has a resistance. And what transmission loss says is that if the resistance of this connection gets big enough, the voltage across this wire representing your signal is going to start to decay, and you're also more susceptible to interference. So that means you can't be more than a certain distance away from the central office in order to have DSL. And because of this noise as well, you also resulted in a lower bandwidth. Now, that was good for the earlier days of internet access in a home environment. This is what a twisted pair copper wire looks like, which was the basis of your home network using DSL. And you'll notice here you have 4 pairs of copper wire, and they're twisted. This is what a network cable looks like on the inside. This in particular is Ethernet or Category 5 cable. And cell line, once you got your connection inside, you could have your copper wire inside, but the phone copper wire was used, twisted pair, to transmit your data. And it's really just taking your data and making it look like sound and putting it at a different frequency. So this is a cable access network, and this is what your Comcast Xfinity product is. Now, this derived from using the cable TV physical infrastructure for the use of sending and receiving data. Now, in the beginning, you have to think back to what the mode was for doing cable TV, right? You mostly got information, your show, your content, from your cable company going out to each one of your cable boxes. And now they took that same physical medium, your coaxial cable, your cable physical media, and they implemented this idea of channels and used those channels to send data from each one of the homes back to the cable company. And so a channel is nothing more than the chopping up of the bandwidth in a communication medium like a wire or coaxial cable in the case of cable into a bunch of blocks of frequency along which you can transmit data. Now, you can transmit this data downward, like the video signals, that's for your content, or the control signal. So when you do pay-per-view, this control signal is what they're using. Or you can have data. So what they did is they took the bandwidth of the coaxial cable for the cable network, and they implemented a bunch of channels, and they used some of those channels for data in order to send and receive your internet traffic. Now, of course, this is what coaxial cable looks like. It's called coaxial, meaning along the same axis. Along the outside of the coaxial cable, if you were to pry open the plastic insulator or sheathing, you're going to see some braided copper on the outside, and then you're going to see a copper wire on the inside, and they're separated by polymer resin. And so you'll notice here the axis along which these two conductors go is in the same direction, hence the name coaxial. And so this is insulation, and the coaxial cable connector looks like the following. You screw this on, and it makes a pretty nice connection. In fact, if you have cable TV, you might have something like this coming into your house somewhere. Now, certainly once you get it to the cable box, you're typically going to have for high-def TV an HDMI cable or something like that. But going into the cable box for your set-top box, if you have cable TV, you're going to have something like this screwed in. So how does cable modem work? It's called hybrid fiber coax. And essentially the fiber part talks about fiber optic strand, and it comes as fiber to what's called the cable head end. And the cable head end is typically in a community somewhere, and it serves about 1,000 to maybe a couple thousand households. And coming out of the cable head end is coaxial cable. But coming into the cable head end is typically fiber optic strand. Now, this hybrid fiber coax can give you asymmetric access, meaning that in the downstream direction from the cable company to the households, you're going to have a higher speed than the upstream. And if you go back to that apportionment of bandwidth, you'll see more of the channels are available for video than there is for data. And the whole purpose of cable modem in the beginning was to deliver data in the downward direction to the homes. Now, it was only later that they added upstream, namely the data from your computer, to the internet. So the internet side, the upstream, is typically lower bandwidth than the downstream. And so you have a network of fiber attaching to the cable head ends, and these cable head ends, output from them to the homes is your coaxial. So you have coax going out, and you have fiber going into the cable head end. Now, of course, this is much faster than DSL, and it's very popular. And this is being supplanted by fiber optic right to the home, which is what Verizon Fios does. And so you have TV and data transmitted at different frequencies over the shared cable distribution network. and you have a cable modem terminating system in the cable head end, and then you have fiber going out. Now, of course, if you drive to communities, sometimes you'll see dotted around the roads and neighborhoods these green boxes. These are cable head ends, and if you were to open one up, and don't open one up, do not ever tinker with communication infrastructure. There are anti-terrorism laws that will come into play if you do. So, but nonetheless, inside of these cable head ends, you're going to find the equipment that takes the fiber signal and converts that out to the cable signal that goes throughout a community. And so this is a cable head end cabinet, and it converts the fiber optic high bandwidth signal to the coaxial signal that actually goes to the individual homes. Okay. And so there are other access networks, the home access network. What happens when you get to the home? Now, typically you have a single connection to the cable head end or to the central office if you're using fiber, and then it comes into a cable modem or a DSL modem in the home. Now, of course, that cable modem would sit somewhere in your house, and you'd also have a router, and that router shares that connection among the different devices in the house, some wired and some wireless. And so this router contains a bunch of other functions, namely routing, the storing and forwarding, firewalling, which is the blocking of channels of communication or the allowing, and something called network address translation, which we'll talk about later on in the semester. Some of them have wired Ethernet. The modern standard today is 1 gigabit, in some cases 10 gigabit per second, as well as wireless, 54 megabit per second, and with wireless N, it's getting even faster. You have some wireless devices, and you often have these functions, this router, firewall, NAT, wired Ethernet, and wireless access in one box. And that's the box that you get from Best Buy for $100 to $200 that you typically call a router. But it's not just a router. It's implementing a lot of other things. It's doing switching, it's doing routing, it's doing access networks, it's doing firewalling, it's doing network address translation. All of these we will talk about throughout the course of this semester. So an enterprise access network is typically Ethernet, and there are other variations for very high-speed access, typically for storage area networks and supercomputing. But these are often used in companies and universities. They, over the time, have gotten a lot faster. A standard right now on campus, as I understand, is gigabit to the buildings and 10 gigabit for the backbone. And systems typically connect into Ethernet switches using a so-called hub and spoke network architecture. And so it's typically the case you have a packet switch called a switch, and those switches allow, and we'll talk about this in great detail, it allows the communication in an interesting way between pairs of devices on the same network, and they're typically connected to a router, and that router eventually is connected to your internet service provider through a so-called institutional link. Now, of course, DSU is paying a service provider for this bandwidth from the institutional link, and you can think of that in a similar fashion to when you subscribe to Verizon or Comcast for your internet access. You pay a certain monthly subscription rate for a certain amount of bandwidth onto the institutional link. Now, an organization the size of DSU would certainly have more than one institutional link just for redundancy, lest some issue happen where this gets congested or this gets cut. Now, this is what a switch looks like for home use, and this is what a router device looks like for home use. And down below, we have what a switch might look like for an enterprise like DSU. It sits in a rack-mounted enclosure and they're much higher bandwidth. This device, a switch, might cost you $100. A router for home use might cost you anywhere between $100 and $300, depending on the bells and whistles you have. An enterprise switch will cost you anywhere from $500 on the low side, average about $2,000, upwards of $3,000, $4,000, depending on what other features you have with it. And also, this is an enterprise wireless access device, and these things will cost you about $1,200 to $3,000, depending on the enterprise features. Now, you might wonder, why am I saying enterprise features? So when you're on campus, or if you are on campus, you'll notice if you have wireless, you can walk around the building and still maintain wireless connectivity. Now, the reason that you're able to do that is because these enterprise wireless access devices will provide what's called handoff or roaming. So if you have two instances of these devices, and let's say one is at one end of the building and the other is at the other end of the building, and they overlap one another in their broadcast radius for their electromagnetic signal information. If you're walking around and you're closer to this one, your signal will go from your device to the local one, and as you walk to the other one, automatically all of these wireless devices, access devices, will coordinate with one another and literally hand off your signal from this one to the other one, so that when you walk through, it's seamless to you, that you don't lose connectivity. You don't get that with a home router. You get that with the enterprise router. And what you're paying for when you pay that $1,000 to $3,000 for one of these is you're getting those types of features where they coordinate with one another to implement roaming and handoff. Okay, so this is the wireless access network, and the wireless access network gives shared wireless access and connects the end systems to your router, kind of like an access point or a base station. And so with a wireless LAN, your radius for connectivity is typically within 100 feet to 300 feet, but that's just an ideal, right? When they test these things, they test them in ideal environments. But what you get in practice is really dependent upon the signal environment, how much other wireless energy is in the environment, also the construction materials. So something like a wood home, wireless passes through wood very easily, but if you have something with a lot of concrete around, wireless does not pass through concrete structures very well or as well. And so there are different standards, 802.11, B, G, N. Different wireless standards differ in the transmission rate. And so what they've done is develop different signaling information where you can pack more bit information in smaller chunks of units to get a higher bandwidth and throughput. Now, of course, there's wide area wireless access, and this is provided typically by telco. And at the moment, 3G and 4G is very popular. 5G is being rolled out now, so it's very, very exciting. You're going to get Wi-Fi types of speed over the wide area, and those deployments are happening now. So when a host sends packets or units of data, these units have a name. They're called packets more generally, but we'll learn later on throughout the course of the semester that these things adopt different names depending on what their purpose is and what layer is operating on them. And so you have an application, whether it's video from a video camera and a video conference like we do on WebEx, and this application takes its message data, it's broken down into smaller units called packets. And each packet has a length, and the standard adopted in the book is L many bits. And this L many bits for each standard unit of data is transmitted into the access network at a certain rate, and that rate is R. Now the units of R is bits per second, and it's going to be really, really important for you to understand the units associated with these calculations. And so the link transmission rate corresponds to its capacity, the maximum amount of data that it can send across a wire. And so one of the things that we're interested in when you talk about communication is the transmission delay. How long does it take for a piece of data, our packet, to go from one part of the network over a link to another part of the network? And this transmission delay is the time needed to transmit an L bit sized packet. And so we have L bits divided by R bits per second. And if you take the units, that's bits over bits per second, right? In the denominator, that flips. So you get bits over bits times second. The bits cancel, and you're left with seconds. So it's going to be really important for these calculations to make sure you're managing your units. And so given a packet of size L and in bits and a transmission rate for a link of size R, or rate R, bits per second, the transmission delay is going to be L divided by R, or L upon R, many seconds. And so when you have your physical media, the bit is what transmits between the sender and receiver pair of the physical media. The physical link is what lies between the transmitter and receiver. And so when you think about it, you have your transmitter, You have your receiver. The transmitter is the one sending the data. The receiver is the one getting the data. And so you have your packet, and your packet is divided up into a number of bytes. Each byte is a number of bits, 8 bits. So you take each bit and you go in a certain order, and let's say it's a 0, 1, 0. So first you send the 0 bit. 0 bit gets sent. And then you send the 1 bit. 1 bit gets sent. And then you send the 0 bit, the next one. 0 bit gets sent, and so forth. So you're transmitting bits at a time, 1 bit at a time, between the transmitter or the sender and the receiver. And the physical link lies between the transmitter and receiver. And there are 2 types of media. The so-called guided media, meaning that the signal stays on that physical link. When you have a wire, that signal is a voltage in a certain frequency, so it's current, and it does not leave that particular physical media. That's things like copper wires, things like fiber optic strand. When you have unguided media, that means your information can flow in all directions. That's what an antenna does. When you're transmitting from an antenna to another antenna between the sender and receiver, the transmitter and receiver, that signal data is going in all directions, right? So this guided media tends to be higher bandwidth than the unguided because you're going to get reflections, you're going to get interference, and so forth. And so twisted pair has 2 insulated copper wires of various bandwidths depending on the engineering that went into it, the standards, and other types of insulation. Another type of physical media is coaxial cable. We talked about that. It's bidirectional, and it's using hybrid fiber coax networks. It's guided media. We also have fiber optic cable. Fiber optics are glass strands that carry light pulses, and each pulse represents a bit for different frequencies of light. It's very high speed because there's very low interference. And it works on the principle of total internal refraction. You take a laser and you pulse it at a certain rate, and then depending on the rate of pulsing, it's a different frequency, and you send that through a glass strand, and it comes out the other side of that glass strand. And there's very little interference with it, and so you can get much higher bandwidth because you can pulse it at a faster rate, implementing a higher bandwidth transfer. And so for radio links, the data is carried in different frequencies of electromagnetic signal information. There's no physical wire, which is good, so you don't have to run wiring all over the place. It's bidirectional, but it's very susceptible to the physical environment around it. So if you have reflections, it might think that electromagnetic energy that bounces off of an object and comes back to you is an original signal. So you have to detect both original signals as well as deal with reflections. And there are different types of radio links. There's terrestrial microwave, which is pretty good and typically used to connect buildings together, like the Living Learning Commons down the street from campus to the rest of campus. There's Wi-Fi, which is local area network. There's wide area network, like the cell network uses 4G and soon to be 5G. And then there's also satellite when you want to send a wireless signal across a really large area, for example, from one side of the country to the other. Now, satellite internet is typically used in rural areas where it's not cost effective to run wires for several miles just to serve a small number of households, for example. So with that, we have covered both the beginnings, class mechanics, as well as talking about the components for the network. And we will turn our attention next time to the network core, covering packet switching, circuit switching, and so forth. So with that, we will end there. And I wish you welcome back to campus. Happy New Year. And COVID is pretty serious, so please stay healthy, stay safe, and I'll see you all on Thursday.